Chapter 10 is all about gases and the gas laws that we have that are going to be telling us the physical properties that we'll see of certain molecules that are primarily in the gas phase. So far throughout our discussion, we've been building up molecules from the electron cloud all the way through quantum numbers, and then seeing what types of bonds those electrons can make, and we've made molecules. Now what we're going to see is a series of chapters that is going to focus on our states of matter. We're going to start with gases. Gases tend to be the most straightforward. What is a gas? Gases, again, are going to be composed of materials that are moving randomly at a very fast in their container. What we want to remember from earlier chapters was the idea that gases have that variable volume and variable shape, which means that they take the shape and volume of the container that they are in. So when we see gases, they are the only one phase that is compressible. We can actually change the volume of a gas by making a container bigger or smaller. And we also can change the shape that a gas contains. They fill up the container that they are in. And so when we think about gases, the primary theory that we will have is the kinetic molecular theory. Now, with this theory, we have a few postulates, a few statements that we have to assume, and we assume these in order to keep our calculations simple. The first one that we're going to see is that gas particles move in a straight line until they collide with either the container wall or another particle, and then they bounce off. Now, we will assume that they are in constant motion and that matter is particulate. It's very small and its volume is independent. Yes, we do know that atoms have mass and have a volume, but when we look at those gas particle volumes, what we are going to assume is that the volume of a container is going to be bigger than the volume of the actual gas particle itself. Now, when a gaseous atom or molecule exerts a force when it collides with a surface or a gas particle, that's what creates what we are going to call pressure. Now, with pressure, we are going to see that it is very important to understand in order to understand actually this kinetic molecular theory. So we're going to first talk about what is gas pressure. Gas pressure is, by definition, a force exerted per unit area by a gas molecule as they strike the surface around them. We are going to primarily look at those gas particles hitting the surface and bouncing off, hitting the surface and bouncing off. And when they do hit the surface, that is with a force, and it's over a unit area. That force divided by the unit area is equal to pressure. So we'll see that in its calculation, and we'll be able to see that when we talk about the overall units associated with pressure. So again, constant movement, but pressure is going to depend on several factors. We will see these factors repeated over and over and over again. The number of gas particles in a given container, the volume of the container, and the average speed of that gas particle. Now, gas pressure as it's compared to the kinetic theory of gases, we're going to start our theory relatively early in this lecture. And the reason for that is because all of our laws can be explained in statement forms, right? A law is going to be a statement of that says what happens, but I also want us to dive into the theory already and explain why does it happen. And if we can do that within the individual gas laws, we can start to see the beauty of kinetic theory of gases. So according to the kinetic theory of gases, collisions of a gas and other surfaces are to be elastic. They are going to be consistent. It means no energy will be lost when that collision occurs. So we can think of billiard balls, right? We can think as these balls start to collide and hit, we're going to assume that as they bounce off, they're going to have that same exact velocity that they had before. Again, constant motion. An inelastic collision is one where particles maybe collide and then get stuck and stop moving. We will not assume inelastic collisions. Yes, inelastic collisions do happen in real life, but this is not a physics class. This is chemistry, and we're going to be basically interpreting the kinetic theory of gases. So if we assume elastic collisions, constant motion, no energy lost, we'll have a lot better time with this. So what is pressure dependent on? Concentration of gas molecules, the number of gas particles in a given volume. We haven't really discussed concentration yet. We will in later chapters, but a concentration is just going to be able to say how many particles are there in a given volume. And so when we look at these two containers, what we want to be able to see here is that the one on the left is at a lower pressure because there are less particles in the given volume. Notice the jar on the right-hand side has the same exact volume, but a lot more dots. And that increase in gas particles means that it's a higher concentration. So the more gas particles you have, the higher the density, right? The higher density relates to a higher pressure. There's going to be more particles, more collisions, and that's how we're going to start looking at the kinetic theory of gases. We're going to look at what does this mean for the number of collisions, because at the end of the day, pressure is generated by collisions. And if we can relate those two right off the bat, we can kind of understand our general idea of the kinetic theory behind gases as well. Now, the kinetic theory of gases is also called the kinetic molecular theory, oftentimes. I want to write out our postulates, our assumptions that we will have in this chapter. The first one is going to be looking at what we said before, that matter is particulate, meaning it's very small. It's small enough that the volume of matter is independent for this kinetic molecular theory. The mass is important, but the volume of the actual particulate, the actual matter itself, is small. So when we're discussing volume, we are going to be discussing the volume of a container that the gas is in. Second one is we are going to assume constant motion. Those elastic collisions. Another assumption is that the average kinetic energy is going to be directly proportional to temperature. Now, how do we know this? Is when we're looking at the joules associated with the kinetic energy. As we increase the temperature, or we'll use Kelvin, we will see that joules increases as well. Thermal energy is related to kinetic energy. A good calculation to remember is kinetic energy is equal to 1/2 mass times velocity squared. So what we see with this equation is that kinetic energy is dependent on both mass and velocity. M is for mass, V is velocity. Lighter atoms may move faster, but they have the same kinetic energy as heavier atoms that may move slower. So higher mass tends to mean higher kinetic energy. Higher velocity can also mean higher kinetic energy. So when we're looking at these three things, we're going to start to see how they encompass the overall theory behind gases. Now, I'm sure we've heard of atmospheric pressure before. We'll dive into atmospheric pressure a little bit. What we want to be able to discuss here is the idea that when we look at different areas of the world, just on this map, we can see low pressure regions, high pressure regions. We know that if we increase altitude, we end up having lower air pressure. As we decrease altitude, pressure tends to increase. So what's going on? Well, the variation in pressure in the Earth's atmosphere is what actually creates wind, and the changes in the pressure help us predict weather. So when we're looking at our air, our atmosphere, what we want to be able to understand is that we have in our atmosphere multiple different gas particles. And as we think about increasing altitude, we actually have to relate that to the number of gas particles that we have in a given volume. If I go up to Mount Whitney, which isn't too far from here, I actually, at 14,000 feet above the sea level, have a lot less air pressure than if I went all the way down to the lowest part of the upper hemisphere is Death Valley. In Death Valley is Badwater Basin, which is about 200 feet below sea level. That would be the highest pressure. When we think of the number of gas particles in those two different regions, there are less gas particles up on the top of Mount Whitney than there are way down in Badwater Basin. And so what we want to think about with the changing of atmospheric pressure based off of sea level is how much air particles are actually around us. And so that's what can kind of help us understand the changes of atmospheric pressure. Now, these ideas can be related to a sample of gas as well. We're just simplifying the situation a little bit. Now, pressure units. When we think about pressure, what I also want to be able to relate are the units. Because remember, a number is only identifiable with its units. So, pressure. We already know it's dependent on gas particles. It will also be dependent on volume and temperature. But here's our pressure definition in equation form. Pressure is a force exerted over a unit area. What does that mean? Well, we can think about pressure as a force, Newton, over a unit area, meters squared. Now, in chemistry, we don't usually like dealing with newtons and meters squared. That's a lot of physics in our minds. So what we can use instead is 1 Newton meter squared is 1 Pascal, PA. Now, again, a Pascal is a relatively weird number for us chemists. 1 ATM is found to be 101,325 pascals. We tend to use in chemistry the ATM. Why? It's because it's the perfect value of the unit. It's not too big, it's not too small, and it can be utilized throughout the entire world. The variations of the ATM are precise enough, but not so precise that we have these trailing values here in these rather large numbers. Now, with pressure units, what I also want us to think about is how actually pressure is formed. And so when we think about pressure, the first thing that I want us to think about is a barometer. Now, way back in the day, a mercury barometer was created by taking a petri dish filled with mercury. Mercury was chosen. They at that time did not know that it was poisonous, but Mercury was chosen because it was the very highly dense, lots of mass with very little volume, metal and liquid at room temperature. And if you take an inverted test tube that's in a vacuum, so not a lot of air in there, put some gradations on that, like a graduated cylinder, you can actually see that the air pressure forced down on the open mercury in the petri dish, and it causes mercury to rise up into the vacuumed graduated cylinder. Now, the first person to actually investigate this was Evangelista Torricelli. Now, Torricelli was an Italian physicist and mathematician. He worked under Galileo. And what he was working on, what he's best known for, is his mercury barometer. Now, with this barometer, what he was actually trying to investigate was suction pumps. And he ended up inventing the barometer. The barometer is named for the Greek word baros, meaning weight. And what he did was he actually created the first vacuum. How he created this vacuum in here was he filled a meter-long test tube with, meter-long, right? Huge, with mercury. He used mercury because the Galileo was not having great success with water. And mercury, like we said, it was a high dense metal. It's 13 times more dense than water. And so he filled up this meter-long tube, sealed off at one end with mercury, and then he tipped it over vertically into a basin, like a open petri dish. And what it caused was the mercury then fell down and created that vacuum space, the head space at the top that we see there. And so then what happened was he was observing this, and every day the level would rise slightly or lower slightly depending on the day. Cloudy day, kind of chilly, the volume would lower. Kind of hot, a little bit more sunny, the volume would rise. And so he started recording the volumes on that tube. And what he noticed was that on average, there was 760 millimeters of mercury in the tube on a given day. Now that number is atmospheric pressure, and he described it that we live in a sea of air pressing down on us. I think that's a nice description. What we know today is that 760 millimeters of mercury is our 1 ATM. So yes, that millimeters of mercury is not a force exerted over a unit area, but it is a measurement based off of air pressure, the particles of air exerting their force over the area of the open container of mercury, pushing up that mercury up the open test tube or the graduated cylinder to create a distance. And so that millimeters of mercury is actually the distance associated with that. Some other pressure units that we will see is the torr, which is the exact same thing as a millimeter of mercury. You can name a unit after yourself if you do all of that work. All of these conversions between pressure units you will be given. You do not need to memorize the torr, the millimeter of mercury, or the Pascal. A couple other ones that I would just want to present for us. We'll do this one. 14.7 psi is 1 ATM. That one's helpful just for us in the United States because we do imperial units, not the metric system. Most of our calculations will be millimeters of mercury, torr, or ATM. The only reason why I present this one is because of lab. Okay. Again, here are some more pressure units. There's the 14.7 psi. These would all be equal to 1 ATM, which is the average air pressure at sea level. Lovely. Inches of mercury, you might see a lot when you are dealing with looking at pressures in the lab, or if you're Googling the pressure of the day, if you end up getting a weather station in your life, you might see inches of mercury if we're in the United States. But again, for our purposes in chemistry, we want to stick with the atmosphere or the torr or the millimeters of mercury. Again, all of these common units of pressure, conversion factors, they'll be given to you. Now, a manometer is a type of or a offshoot of the barometer. It looks similar to the barometer. Why it's important is that you can actually test for a sample of gas pressure. So what we see here is a U-tube. This U-tube is open to the atmosphere right here. It's in this U-shaped bend with mercury. Again, mercury being highly dense metal at room temperature, and a liquid at room temperature can be very helpful for our atmospheric and sample pressures. And then we have a sample over here. So we're not just measuring the atmospheric pressure. What we actually can now measure is the difference between the atmospheric pressure and a sample pressure. Competition is established. So as we are starting to see the atmosphere push down on one end, the sample is starting to push down on the other end of that mercury. The difference in height indicates the pressure difference of the atmosphere to the sample. So our change in height, usually in centimeters or millimeters of mercury, depending on what type of a manometer you have, indicates the actual change of pressure in millimeters or centimeters of mercury for the atmosphere versus our sample. So it's highly used in the laboratory for quick sample pressure readings. All right, so we said that there are going to be some dependent variables for the gas pressure. First one that we talked about was amount of moles. We mentioned temperature a little bit, and now we're going to also talk about volume. So all of these four basic properties of a gas are going to be interrelated: pressure, volume, temperature, and moles. We are going to use the abbreviations P, V, T, and N. Pressure is going to generally be in units of ATM, volume in liters, temperature in Kelvin. It always has to be in Kelvin. The reason for that is we definitely do not want any negative values encompassing our ideas of pressure, volume, or moles. They cannot be negative. So temperature cannot be negative. And moles are just moles, abbreviated N. So how are these properties interrelated? Well, when one changes, it definitely is going to affect the other ones. Our simple gas laws will show us the relationship between these pairs. We'll dive into the simple gas laws now and see how they interrelate to the overall ideal gas law. Now, Boyle's law is the first one. It investigates pressure versus volume. Now, when we investigate this relationship, we have to keep constant the other two variables. So temperature and moles will be constant in Boyle's law. For Charles' law, he is going to investigate volume versus temperature relationships. So what we have to keep constant is pressure and moles. Avogadro's law investigates volume and the mole relationship. So we have to keep pressure and temperature constant. And the Guy-Lussac law, which is kind of in your textbook, but not really heavily investigated, I'll treat it just as we did the other one. He investigates pressure and temperature. So what he is holding constant is volume and moles. All right, let's dive into these very basically. But when we look at these, I do want to present the idea of the kinetic theory of gases as well. So we'll explain the why here. Just remember, the law explains what happens. The why is the theory. So Boyle's law. What Boyle says when he investigates pressure versus volume is that, well, if I were to think about a piston which has a variable volume, and let's just put 5 gas particles in there. Now let's decrease the volume and put the same 5 gas particles in there. What's going to happen to the pressure? As volume decreases, the walls of the container get closer, and so the gas particles will reach the sides of the container faster. They will be able to exert more forces over a unit area in the smaller volume, and so pressure increases. Why this occurs is because of an increase in collisions. For the kinetic molecular theory, a decrease in volume is increasing the number of collisions, which is directly related to pressure. The same thing goes if we were to increase the volume. If we increase the volume, the sides of the container get further and further away, and therefore we don't have as many collisions. So as volume increases, pressure decreases. These two are inversely proportional. As one increases, the other does the opposite. Now, in order to calculate these, the equation we have for that relationship is the multiple. P1 times V1 is going to be equal to P2 times V2. How we would use this is that if we said the volume of a container initially is 1.0 liters and 752 millimeters of mercury, what happens to the pressure if the volume increases to 2.5 liters? We can estimate, or we can kind of hypothesize here that when we are looking at this relationship, that, okay, if the volume increases, I know my pressure should decrease. Let's do this math to see. The volume of 1 times its pressure is equal to the next situation's pressure times its volume. Units can be in whatever you like for pressure, volume in this relationship, because as long as they cancel, your units just need to be consistent. So what we should be getting here, 301 millimeters of mercury. Pressure did decrease as the volume increased. For law number 2, what we want to be able to look at is Charles' law. Charles's law, remember, is a volume and temperature relationship. Now, in order to do this where we're keeping pressure constant, the best relationship is to look at a balloon. Let's put a couple moles in there and say, all right, I'm throwing a birthday party and I want to have this balloon at room temperature, 298 K. Let's just say that the birthday party gets a little crazy. And I go ahead and throw this balloon in the fire. Oh my goodness. There's the fire. We'll make it red. And we can assume, hey, let's let that temperature go up to 1,000 K. Crazy party, right? What's going to happen to the volume? Well, let's think. If temperature increases, the gas particles, remember, increase their kinetic energy, increase their velocity, their movement. And so they are reaching the sides of the container faster. Now that exerts a pressure. We don't want pressure to change. So what happens by default is that as those particles start to increase their velocity, increase the number of collisions, the sides of the container must move out further, creating an increase in volume. Big V. So temperature is directly proportional to volume. When we look at that equation, what we'll see is that it's slightly different. It's going to be V1 over T1 equals V2 over T2. As one increases, the other also increases in the same proportionality. So dividing volume by temperature, we'll get a constant. Moving on to number 3, Avogadro's law. Who investigated moles versus temperature? Oops, excuse me, volume. Again, I'll use the birthday balloon idea. Put some moles in there, 3 little gas particles. What happens if we wanted to blow that balloon up a little bit further? What would happen if we wanted to put in another breath of air? Let's say 6 moles. As the number of moles increases, the number of particles exerting force over a unit area also increases. The collisions would increase. But again, we don't want those collisions to increase. So what we have to do is increase the volume of the container. Again, moles and volume are directly proportional. As we increase the moles, they need more space. And so therefore the volume will increase. The equation looks very, very similar from before. V1 over N1 equals V2 over N2. For the Gay-Lussac law, we're looking at the difference between pressure versus temperature. Again, now what I like to think about for this one, we can either think about a soda can or a spray bottle. I'll just do a soda can. Soda. That's closed, right? Now, in a soda can, usually it's about 4.4 atm of gas in there. Carbon dioxide is the gas of choice because of the carbonation that we know of in soda. Now, if we were to leave that soda can in the car, and let's say increase the temperature, it's a hot, steamy day. What's going to happen to those particles if we were to increase the temperature? Well, let's just put it over fire. Why not? We can pretend it's a crazy party again. Now, if we increase the temperature, again, the particles' kinetic energy is increasing, their velocity is increasing. Now the sides of the container cannot increase, so collisions are increasing, which means pressure will increase as well. Temperature is going to be directly proportional to pressure. And when we look at that calculation for the simple gas law, we see it's very, very similar to our other proportional relationships. So it's all about what is the variable doing to the number of collisions, increasing it, decreasing it, and then therefore what happens to pressure. And if we're keeping pressure constant, we can relate it back to volume. So with these individual gas laws, those are really helpful, but not in a holistic picture of a gas. What we need is the ideal gas law. And so we've combined all of these individual laws to say, instead of a simple gas law, Boyle's law, Charles' law, Avogadro's law, where we're keeping something constant, why not identify a holistic picture of the sample of gas and say, what is the pressure, volume, moles, and temperature of a specific gas sample? And that's where we get the ideal gas law. Now, R is incorporated in there because this is now no longer a proportionality. It's an equals, PV equals nRT. Now, that R is a constant that will always be given to you, and it's 0.0821. Now, some books have 0.08206, just spreads out one more sig fig on that value. Because this is a constant, you do not need to know the sig fig values, but you can use either 821 or 8206. Either one is appropriate. What we will want to be able to notice here is the units of R. Liters times atmospheres over moles times Kelvin. So with the individual simple laws, the units don't necessarily matter. The only one that matters in the individual laws is temperature for reasons we explained before. Temperature can't be negative, so it has to be in Kelvin. But now with the ideal gas law, we see a very specific idea here with the units of R. And so therefore, pressure has to be in ATM, volume has to be in liters, N is in moles, and temperature is in Kelvin. And so we'll be able to utilize this idea and understand how does a sample of gas look like in all of these physical properties: pressure, volume, moles, and temperature. Let's just revisit our kinetic molecular theory one more time and understand the idea behind it, that we are going to be focused on collisions. Again, elastic collisions occurring between volume irrelevant gas particles that are traveling at a constant motion. All of those things we're going to understand. So force equals mass times acceleration. We can also say that the force is equal to mass times the change in velocity over change in time. Again, elastic, right? And so when we look at the number of collisions, we can say that they are proportional to the kinetic energy and proportional to temperature. And this is the overarching idea of why the simple gas laws work. Force equals mass times acceleration. You can go through that derivation that gets you to the idea of mass velocity squared. Not necessary at this moment, but what we want to be able to understand is this factor of the idea that the number of collisions is going to be directly related to kinetic energy and therefore the temperature as well. So if you can relate any of those simple gas laws to collisions, that's how you explain the kinetic molecular theory. All right, standard conditions. Because the volume of gases vary with pressure, temperature, and moles, so chemists have agreed on a set of conditions so that when we report something in a scientific paper or even in just discourse and communicating, we have some standard ideas. Now, standard pressure is 1 atm and standard temperature is 0 degrees Celsius. This one's very important. Some people say that it's room temperature. They're not correct. Room temperature is not a standard unit. Some rooms are 25 degrees, some are 22 degrees Celsius. So when we're looking at a standard temperature, we are taking 0 degrees Celsius as our standard. With these two, you might see something that says STP, standard temperature and pressure. That's a very simple way of saying 1 atm and 273 K. That's a good one to remember. You will not be given those as standard conditions. If I say something is taken and measured at STP, that means standard temperature and pressure. You would have to know what those mean. 1 atm, 273 K. A standard amount is 1 mole, and a standard volume, if we were to plug those three into PV equals nRT, turns out to be 22.4 liters. So rearrange PV equals nRT here, put in the standard pressure, temperature, and amounts, and that's how we came up with a standard volume. Now, definition of that standard volume, it's the volume occupied by 1 mole of a substance at STP, and it always turns out to be 22.4 liters, no matter what the sample is. So the volume of 1 mole of gas is actually 6.022 times 10 to the 23rd molecules of that gas, right? And remember, that is immaterial of the type of gas. That means it doesn't matter the size of the gas particle, it doesn't matter the mass of the gas particle. If you have 1 mole, you have 22.4 liters of it. So noticing these three balloons in these 3 gas tanks, when we are looking at STP and 1 mole of a gas, the standard molar volume is immaterial of the actual masses. We have 3 samples of gas here with 3 very different molar masses or atomic masses, but they all produce the same volume. Now, a density of a gas can be taken. The only issue with the density of a gas is density is usually mass per volume, usually grams per milliliter. Now, because the gas is so light compared to its volume, we usually report density in grams per liter. Again, it's still density, it's the amount of mass per unit volume, but the unit of volume increases slightly so that we can be able to work with the number and it's not too small. Now, we can look at density. Its abbreviation is D. But again, density grams per liter. We can look at a couple of different things here. Now, the mass of 1 mole is a molar mass, right? Grams per mole equals the molar mass. These are all useful conversion factors that we've seen before. Density equals mass over volume. I'll use grams over liters. And we're going to try to interconvert with these in order to come up with something calculable with PV equals nRT. So if we wanted to calculate a gas density, this is the derivation. First, what we would just say is rearrange that so that we are moles over volume, right? We just do some math to put volume over here, RT over there, so that we get N over V, moles over volume, is equal to pressure divided by RT. Now, what we want to replace is the idea that the number of moles is actually the grams divided by the molar mass, capital M, as your book likes to use. That idea came from what we previously know is the molar mass is equal to grams divided by moles. Lots of derivations, just lots of algebra, rearranging things and plugging them in. Well, if we know the sample grams over volume, that's density, right? So just rearrange this. Molar mass gets rearranged a little bit and put on the other side. I like to use double M, molar mass. And what we'll see is that the density is actually equal to the pressure times the molar mass divided by RT. So even though the molar volume is consistent at standard temperatures and pressures for every sample of gas, no matter its identity, the density of that gas is different. The density of the gas is directly proportional to the molar volume or to the molar mass. So we can utilize this equation anytime we have a sample that we would want to identify its density for. You would not need to know that calculation. It would be given to you. PV equals nRT, you should know. Grams per mole, you should know that that's a molar mass. So you could always derive this equation yourself, but it's not one that I make you memorize. All right, one more law that we want to be able to look at is looking at mixtures of gases. Now, many gas samples are not pure, but mixtures. A great example is just air. Air is mostly nitrogen gas. Oxygen makes up 21%, thank goodness for us. Argon, a little bit there, 0.9%, and a very, very small amount of carbon dioxide, changing every day because of climate change. But this is a decent composition of dry air. Now, when we say dry, because we don't want the moisture component, water vapor would just add one more component to this. So we'll keep it simple and say dry air. Now, when we look at this percent by volume, we can actually utilize this and understand partial pressures. In certain applications, the mixture can be thought of as actually one gas. Why? Well, think about it. This volume of the container is consistent. The temperature in here is going to be consistent. Not the pink particles can't be higher in temperature than the blue particles or the green particle. The temperature is all the same. And so when we look at that, the only difference between the colored particles is moles and pressure. So what we actually can start to look at is the different compositions of moles and relate it to the different pressures, or what we call partial pressures. A partial pressure will just be defined as the pressure exerted by a specific gas in a sample. We can still identify the total pressure of the sample by adding up all of the moles, but if we wanted to look at partial pressures of a sample, we turn to Dalton's law of partial pressures. Now, Dalton's law states that the total pressure of a gas mixture is equal to the sum of all of its partial pressures. So if we had some nitrogen exerting pressure and some oxygen exerting pressure and some argon and a little bit of carbon dioxide, the individual pressures of each of those gases is going to be additive for the total pressure. Now, the particles have a negligible size and they do not interact with each other. We're assuming that all gas particles are independent of each other. Yes, they might have different masses, but they have the same average kinetic energy at this specific temperature. And so even though some of them might weigh a little bit more and their size might be a little bit different, we're going to assume that that difference is negligible, because in reality, it's very small. Because the average kinetic energy is the same, the total pressure of the collisions is the same. So partial pressure of a gas, usually abbreviated P sub whatever gas we have. That's what we will call the pressure of a single gas. So if we look at this sample right here, I have some blue gas particles, which I've labeled A. They will exert pressure sub A, PA, or the partial pressure of A. The purple ones, what I'm calling B, will be partial pressure of B, or pressure sub B. Now the sum of these added together, PA plus PB, is going to be equal to P total. Because each individual gas particle is hitting against the sides of those containers, independent of one another, in elastic collisions. And again, the volume of the container is going to be the same for the blue and the purple gas particles. Can't change the volume for just the purple, can't change the volume for just the blue. The temperature, again, going to be consistent for all of those. What is different is the fraction of the mixture it composes. There's more blue particles than purple particles, how I drew the diagram. So we can assume that the partial pressure of A, the blue particles, will be higher than the partial pressure of the purple particles. B, The reason for that is how I drew this. The moles of A are greater than the moles of B. So focusing on the moles here will be important to understand Dalton's law of partial pressures. So for a multi-component gas mixture, we can calculate the partial pressures of each component using the ideal gas law, PV equals nRT. But what's important is that we use just the partial moles. These P sub A and P sub N are partial, looking at just one component. We can do that for every component. Notice that we've identified the idea that RT over V is not partial. It's for the holistic picture of the sample. And again, the total pressure is going to be additive. For a mole fraction, this is also very, very important because we can assume that RT divided by V is constant for every sample of a mixture of gases. R is a constant, T is going to be constant for each individual gas particle, and V is also going to be constant. So what we've done here is we've taken the ratio of the partial pressure to the total pressure, which is going to be equal to the ratio of the partial moles to the total moles. This is what we call the mole fraction, or chi in Greek. Now, the partial pressure to the partial, or to the total pressure, or the partial moles to the total moles can be equal to the mole fraction. That's what we call it. Now, in this mole fraction, again, we can be utilizing a couple of different things. We can utilize this equation or the previous one. I'll rewrite it here, to investigate different parts of a sample. So let's go back to air. If nitrogen has a 78% composition in air, and remember this was by volume, what can we assume for its partial pressure? Well, that percentage tells us the percentage that nitrogen is in the air. It actually tells us the fraction just in volume portions. But if we were to look at nitrogen, we can understand its partial pressure is 78% of the total pressure, or 0.78 atm when we're at atmospheric pressure, 1 atm. So we can utilize a percent composition by air, we can utilize the mole fraction to start to investigate the partial pressures according to Dalton's law. Where this is important, outside of looking at the composition of air, in the lab, sometimes we often collect gases in a reaction, specifically when we drop a metal in acid. So this reaction right here, it's expressed with zinc and HCl. Now what happens here is H2 gas is produced in this reaction. Overall, we can see zinc and HCl reacting to produce H2 gas and zinc chloride. Now, when we look at that reaction in the lab, we want to be able to collect this product. H2 gas is important. Let's not have a Hindenburg in the lab, right? We don't want things to explode, so we might need to collect this H2 gas so that we can isolate it. Now, when we collect this gas, a typical setup is the one you see on the right-hand side, collecting gas over water and having them displace water from a container. Now, when we do this, what happens is as our, if we can see, as our gas particles are shifting themselves through and bubbling out into the volume of water and creating a headspace, it's hydrogen gas plus water vapor. And so we'll see these partial pressures calculations in a lot of collecting gas type situations. So a table can be used to find the partial pressure of water. We know the partial pressure of water that appears in this headspace is going to be proportional to its temperature. And so what you'll see is the table in the next slide that would be given to you if you needed it. But when a gas sample is collected over water, the gas sample total pressure will incorporate not only the gas that you wanted, but also the water vapor pressure. We can look at a couple of numbers here. As the temperature changes, as we increase that temperature, what we notice is that the pressure increases as well of the water. So be very, very careful in the lab when you are collecting a gas over water to note that the pressure you measure is not the individual gas partial pressure, it's the total pressure. So it will be the pressure total, which will be equal to the pressure of the gas you wanted to collect plus the partial pressure of the water, which you can find in this table. All right, so kinetic molecular theory. Just a review before we end today. The simplest model for the behavior of gases is the kinetic molecular theory. In this theory, the gas is modeled as a collection of particles, either gas, molecules, or atoms, depending on what we're looking at. Methane, CH4, is a molecule, but helium, He, is an atom. But either way, they are in constant motion in elastic collisions, right? And the attraction between the particles is negligible. We never talked about the gas particles hitting each other and sticking because we assumed elastic collisions, that they will not stick, they will just bounce off of each other and bounce off the sides of a container and have no attraction between separate particles. This is a fine way to handle our gas laws because we get a very easy PV equals nRT ideal gas law. But in reality, do these postulates actually work? Yes and no. We like to think about the average kinetic energy of the gas particles being directly proportional to Kelvin, so that as we raise the temperature, we're raising the average speed of the particles, and therefore, yes, the collisions increase. But remember, not all the gas particles are moving at the same speed. They do have different velocities, same kinetic energy, just different velocities. So yes, there are going to be some issues with the kinetic molecular theory. The collision of one particle with another is completely elastic, but we know that kinetic energy technically could be lost by one particle and completely gained by another. And so these assumptions are not real behavior. Because real molecules do take up space, the molar volume of a real gas is larger than predicted by the ideal gas laws, specifically at high pressures. The higher the pressure, what we see as pressure increases here, we actually see that the molar volume does change. And so at high pressures, we deviate from ideal behavior, and we get real behavior. Another issue is as temperature decreases. As we get lower and lower temperatures, we start to see attractions between the molecules. So over here at low temperatures, we start to see deviations. Again, low temperatures, high pressures, we get real things happening. A couple of attractions that we'll talk about later on in the second semester of general chemistry is the van der Waals attractions. All we would need to know for these now is that there are molecules that attract other molecules. It's called intermolecular forces of attraction. Van der Waals occurs in every particle. Every molecule has van der Waals attractive forces. There's a slight attraction because everything has electrons and protons. Now, you do not need to know the corrected formula for the intermolecular forces. We are going to stick with ideal behavior, and that's gonna be wonderful. Why? This would be PV equals nRT if we assumed, if we did not assume the things that we already did. We have to correct for particulate volume, and we have to correct for attraction or inelastic collisions. This would be PV equals nRT. What our take-home message here is high pressure and low temperature, we are not ideal. And that's a bummer. But if we have lower pressures, higher temperatures, we can use PV equals nRT. The higher the pressure and the lower the temperature, we're gonna stray. We know that we're gonna stray because our assumptions in the kinetic molecular theory are inaccurate. Well, there's the ideal gas plot right here along the middle. This big old blue line that I'll highlight. What do we get in real life? Nothing that looks remotely ideal, which is unfortunate, but that's what we're going to deal with in this class. The ideal gas law is what we're going to assume. We don't want to deal with anything that strays outside of our ideal behavior. Thank you very much for joining me.